Hello and welcome to this video on quadratic regression on Desmos graphing. When we are talking about quadratic regression, basically what we're saying is that we're going to be starting out with points, x, y coordinate points or x, y values from a table that we could plot on a graph, and then kind of working backwards to determine what type of parabola and what type of quadratic function would match those points as closely as possible. And we're going to be doing that using the Desmos graphing calculator we see in front of us right now. So our first step would be collecting data from an experiment or just obtaining points that we're making up, kind of depending on what you are working on. So the first thing we want to do is hit a plus sign, and we want to add a table to our graph. So you can see we have x sub 1, and that's like a subscript right there, and then we have y. So I'm just going to kind of making up some numbers here so we can start have some points plotted. So 139.4, and I'm just going to kind of fill in our table here with some values to use for our quadratic regression. We want to use at least 3 points for a quadratic regression in order to get a parabola that would to get a parabola that would fit it the best. If we only have 2 points, that's really only enough to do linear regression to find a line of best fit instead of a curve of best fit. So whenever you're doing linear regression, you want to have at least 2. When you're doing quadratic regression, you want to have at least 3. And that continues if you go above quadratics. You generally want to have 1 more point than what your highest exponent is. So if we wanted to see these points on our graph, we need to make our viewing window on Desmos a little bit bigger. So we could zoom out like this, but we still can't see anything. So we want to click on the wrench icon and go down to x-axis. So we don't care about any negative numbers. So I'm just going to have it start at -1 and then go up to above our biggest number. So I'm going to go to a nice round number like 10. And then for the y-axis, I want to start that at -1 and then go above our largest number to the nearest 10. So I'm going to go up to 60. I now have our points plotted, and you can see I kind of even kind of drag it so it looks a little bit different. So now I could kind of go about this in 2 different ways. So the first option would be, do I want my equation to be in standard form or vertex form? So I'm going to go with standard form because most calculators or graphing applications will give you a quadratic regression function for your points in standard form. So my first option is to type a general version of standard form like this right here. And I see how all these buttons come up over here for A, B, and C. It's going to ask basically add sliders. So if I click on all, I can see that I've now added A, B, and C. And I basically would want to just kind of adjust these so that I can move them to kind of fit the points that I have in front of me the best. And sometimes you might not be able to go up as high as you need to, so you can always adjust the range of what your sliders are going to be. So now I can move it all the way up to kind of closer to my values, and I can kind of do this for all of my values and eventually get to an equation that might look pretty close to what I'm really going for. And it's a little challenging to do it with standard form, doing it this way. As you can tell in front of us, we're not very close to our points. So let's say we don't like how inaccurate that is, and we want to get rid of it. So we could also do vertex form. So I would just change this to being a times x minus h squared plus k. And then I would hit all to add all of these sliders. So then I know that my parabola is going to be upside down, so I can make this into a -1 first. And then I know I'm kind of moving over to maybe about 3 for my vertex. And then my k is doing up and down. I need it to go up to 60. So I can say 0 to 60 here. And maybe go up all the way to 60. Oh, well, that's too high. So I can maybe back it down a little bit. And we need it to be not quite as flat. So we need to be a little bit steeper. And so now we've kind of made an equation that matches it pretty well. But this guess and check method is by far not the most efficient way to do this. So let's back up and get rid of what we just were working on and use Desmos more to our advantage. So one thing Desmos can do is actually get the exact equation, our formula, our function that you were looking for that would match these 3 points as accurately as possible. So the way to do that is typing in y, and then if you hit the underscore button and then type 1, y1 is basically representing the y part of our table up there. So next, instead of an equal sign, we're going to hit shift and then look at the button next to your 1 key, and it's going to be what's called a tilde, kind of a squiggly line. I'm sure you could find it on your keyboard in front of you. So now I'm basically going to type in our standard form, but instead of x, it's going to be x sub 1 or x underscore 1. So I have a, and then x underscore button 1, and then I do the same thing with b and c. So now I have made, I forgot to put it as squared. So we've got our squared making a quadratic. So you can see now we have a quadratic that is going through all 3 of our points almost perfectly. And so we have our quadratic equation. If you look at what they gave us, they're giving us a and b and c. So now I could go into an equation down here and type that in. I would do -4 for a, -4x squared. I have 23.7 for b next to x, and then I'm adding 19.7 for c. And you can see that that is going to be kind of matched what our red function was. They are right on top of each other. So that is the regression equation for our table up here. And you'll notice in our regression here, in this red row of our Desmos table here, we have this r squared value equaling 1. R squared, without getting too far into the statistics behind it, if r squared is closer to 0, our curve of best fit doesn't fit our data very well at all. If r squared is really close to 1, or in this case exactly equal to 1, that means that our curve of best fit basically fits our points perfectly and is exactly on top of basically all of our points. So that means that Desmos was able to do this really, really well. So if I were to go up, and we'll get rid of our blue equation. If I were to go up here and change this or change maybe this to just equal to 50 and plot it, well, that would change it a little bit. So then I could change and maybe hit 4 and say that was equal to 40. So now, if we have 4 rows of our table, if we have one point that doesn't quite fit with the rest, Desmos is able to adjust on the fly because of how we have it set up. So now our equation instead would be -5.4x squared plus 27.2x plus 17.8. And you can see that our r squared value is now 0.9936 because our curve of best fit doesn't go perfectly through all of our points. And instead, it kind of goes as close as possible to all 4 of them at the same time. And we could still add more points. Like if I added 5 and 50, we have a parabola kind of going through all of this, and we can see our r squared value isn't quite as perfect as it was before. And so we can kind of add, and this curve of best fit will still fit these points as best as it can. It would just not be nearly as accurate or nearly as close to the actual points as it was before. And you can see how our r squared value is pretty close to 0, so it's not very close to our actual points. And so doing it this way, you can make a table and then use Desmos to get as close of a curve of best fit as you possibly can. And this would be useful in creating a model for real-world data that you've collected to see if the data you have is quadratic in nature, and this will give you the function that you would be able to graph to have that curve of best fit. And that is how you do quadratic regression in Desmos. Thank you for watching.